So, good afternoon, everybody. Thank you. Appreciate you coming out. So my name's Charles Feddersen. I'm a program manager in the Azure Synapse team based in Redmond. I'm joined by my very good friend, Joseph, who's actually one of the engineers who developed the technology we'll be talking about today. So rather than give you the classic PM conversation and talking about features and demos and everything like that, we're fortunate enough to actually have one of the engineers who's going to walk through at a relatively low level how we went and built this brand new distributed query engine that was called, Rohan called it out in the keynote on Monday morning, and how it's enabling these amazing amounts of scalability that we've talked about so far in the conference. So with that, the focus here is really going to be around looking at Synapse and the SQL On-Demand capability within the platform. Now, when I said, so describe how we're going to talk about this, I'll cover the SQL On-Demand capabilities and that exploration and transformation of data at scale over the lake. When Joseph talks about the distributed query engine that we've built for this technology, that actually encompasses all of Synapse, so both the provisioned capacity and the on-demand modes for consuming the service. And we've had a lot of people come by the booth in the last couple of days, and there's sort of some entities we've been talking about. So if we've spoken to you, hopefully this sounds pretty familiar. So just setting expectations, you will have seen sort of this in other sessions. The way to think about Synapse is this is the next evolution of Azure SQL Data Warehouse. We up-level and enhance the SQL technology that was in SQL Data Warehouse significantly, and then we also add a lot of new capabilities like data integration, big data processing as well, and then bring connected services into Azure Studio, such as Power BI, for that integrated authoring experience as well. You will have hopefully seen this in a couple of other sessions. What I really want to call out and sort of draw your attention to is this is really the scope of the session today. So we're talking about writing SQL in an on-demand form factor using one of the SQL engines that's in Azure Synapse today. So I talked a little bit about this already, but the way to think about the separation here, when you're in Azure Synapse Studio and you're running SQL Analytics, you have a choice to make at the top of the developer pane. You have what's called a pool, or a SQL pool, or you have SQL On-Demand. SQL pools you can think of as the classic cluster form factor that you'd be familiar of. If you sort of run VMs and more infrastructure, it's kind of like that. The consumption model is on time per compute provisioned. And so those clusters will sit there, they're dedicated to you. They're really optimized for maybe that traditional data warehouse-like scenario where you've got really high concurrency coming in, lots of users, you're reusing hot caches. The fact that that capacity is dedicated to you means the caches are fully maintained, even when you're not running any queries. So when you walk up again, you get that really fast interactive execution time. On-demand is different. On-demand model is based on the amount of data scanned. And it's more suitable for exploration of the data lake, more ad hoc queries, but also data transformation at scale. And I'll give you an example today of how you can run create table, a select statement over the data lake. And anything you can really do with the SQL language in a select statement, you can apply that to transformation directly over delimited files or even Parquet that's stored in the data lake today. There are really five, let me get to this one first. The way to think about these scenarios is discovery and exploration is really like, what's in this file? Have you ever had to load a file into a database before? Someone's given you a file, and it's like, great, what do I do with this? If it's small enough, you might open it in Notepad. You've got to start figuring out types and delimiters and things like that. Sometimes you might be running evaluations where it's data you've never seen before. And so there are these hassles that often come with exploring new data. I've got new data. What am I going to do with it? And how can I be really efficient in using and consuming that data? The second is around data transformation at scale. What we see is like the economics of cloud storage enable you, this platform, to store all of your data through multiple stages of transformation. It's very rare that a piece of data actually lands in the format with which you're ultimately going to consume it or surface it to your end users. And so we see customers building these architectures using data lakes to say, this is my raw data, this might be transformed or cleansed data, this might be trusted data. And so the data itself transforms, but because of that economics of cloud storage being very cost effective, they maintain versions of it where they can walk the lineage back if there are inconsistencies or audit or scenarios like that. And so the SQL On-Demand capability is a powerful engine for doing that massive transformation at scale as well. There are really five fundamental functions in the SQL On-Demand capability. The first is around, and I'll show this in the first demo, the ability to effectively walk up to a file, sight unseen, right-click it and say, go query this. In databases, this is a little easier because you've got tables, you've got schemas, you've got catalogs, you've got data types. The system knows what it's working with, and so it's pretty easy to sort of figure that out. Files are files, right, unless you actually crack them open. And so we've built some intelligence into the platform to really streamline that exploration scenario. The second is the ability to query files directly. If you've worked with other platforms, and including actually Azure SQL Data Warehouse previously, they had the capability as well to query data in a data lake, but not specifically to query the file itself. And so what SQL On-Demand enables you to do is effectively, and I'll sort of pseudocode here, select star from file.txt before even needing to create a schema over the file. And then with the create table as statement, you can actually infer the schema, and the transformation will automatically generate that for you. You can also create database views. So this is the scenario where I've got data in the lake. I don't want to expose the complexity of this to my end users. So I can write a query directly over files. I can do complex joins. We'll talk a little bit about that. And then I can put a view directly over that, and I can surface that to an end user. I've abstracted all of the complexity and all of the logic. They don't even need to know what a data lake is, because users are very good at consuming database objects, and BI tools are also very good at connecting to an endpoint saying, these are my tables, these are my views, I understand that, I can issue select statements against that. So that's a scenario as well. And then this data transformation manifests in the code create external table as. So what's interesting about SQL On-Demand today is it has a notion solely of external tables, which is to say that I'm creating a schema over files that are stored in a data lake storage account. And so what you can do, though, is you can take a whole bunch of data. It could be one giant monolithic table. It could be 5 or 10 tables that you join together. But that create external table as select will write the output into even Parquet format, if you want, directly in the data lake storage itself. Finally, this shared metadata. So one of the key integration points that we've done is around Spark. And so if you have developers in your organization who are building Spark-based solutions, they love the notebook experience, they want to write Python or Java, or they're even writing Spark.net on Spark. When they go and save something as a table in Spark, and I'll show you what this looks like in a demo today as well, that metadata is automatically synchronized to SQL On-Demand, because the analysts don't really get Spark, with all respect to the analysts, right? They love SQL, they love BI tools. The data scientists love sitting in Spark notebooks. There's always been this challenge of operationalizing the insights that a data scientist might yield to an analyst who wants to sit in front of Power BI. And so now the ability for the data scientist to just produce the output, a whole bunch of predictions or forecasts directly into Synapse, and then SQL On-Demand can just query that with the SQL language immediately afterwards, is very, very powerful for accelerating some of these scenarios. So let me break into a demo early, and let me show you a little bit of what I've just talked about. Here we go. Ooh, I might need the wrong number. Plug it in. Okay, sorry about that. So here I'm in the Synapse studio, and I'm going to just walk, for those who haven't seen it, hopefully many of you have, and you've been past the booth in the last couple of days, you're relatively familiar with it, but let me just sort of walk you through what you can see here. So on the left-hand side, I've got an object explorer where I can look at data, develop, and orchestrate. So data is representing, in this case, my storage accounts, my databases, and then also I've got some data sets for Power BI at the bottom. So here you can see that I'm in a storage account, and I've got a set of Parquet files. They're about 20-something megabytes each. I don't know what's in them. Someone else put them there. They might be useful. I want to take a look at those. So historically, you would need to go and create a schema over these, which means you've got to crack them open somehow. You've got to figure out what the columns and the data types are. If you're being lazy, you won't worry about the data types. You'll just tell it everything's a string, and you'll figure it out later. But what I can do now with Azure Synapse is just say, I want to look at this, so give me a new SQL script. We automatically create the code in SQL to just give me a sample of the top 100. We've automatically populated the location here, and I've automatically determined that it's Parquet. So I can go run this now. Hopefully this comes back in a matter of seconds. And what I'll see here is that I'll get a tabulated response at the bottom. So now what it's actually gone and done as well is it's determined my delimiters. Now in Parquet, this is a little easier. And then shortly we're going to enable support in delimited formats as well. But I knew nothing about this data. In fact, until I look at it, I still know nothing about this data. But the system has given me this incredibly convenient way to go and look and peel back under the covers and see what I've got in my data lake and what I might want to use. So now I'm going to flip over to here, and you can see a different example. So here's one that I ran earlier. So it's the same query at the top. It's a select top 100 that I just clicked and finished. But now I'll show you how I can create a view over that. So I found some data that's useful. We'll run with a relatively simple query in this example, just for the sake of the snappy demo. But what I can do here is I'm going to go and say, let's see if it still exists. Okay, so we've dropped it. Now I want to go and create a view. So now I'm just creating database views, which are just, there's no data in them, it's just a schema pointing directly at the files in my data lake. And so this is going to execute relatively quickly, I hope. There we go. And now I can access it. I don't need open row set, I don't need file or what have you. Now I have a SQL endpoint. The connection string looks just like you would connect to SQL traditionally. So BI tools understand this a common endpoint, a common language. And now I can go and say, I just want to go and run select star here. And this is going to bring me back that result set from the view that I just created. So a really seamless way to operate over data in the lake using familiar languages, a lot of mouse actions and less code. As you can see, I actually didn't write a single line of code there. Granted, I wrote a little bit before the demo. But really, it's a very smooth way to start to analyze and look at data directly over the lake. So with that, I'm actually going to pause and hand over to Joseph and let him now sort of dive into under the covers of this, and you can see exactly what's running and how it works that is enabling this technology. Joseph.
Okay, thanks, Charles, for the introduction. So next, as Charles pointed out, I'm going to talk about the distributed query processor that we have built and powers both the on-demand and provision offers for SQL Analytics in Synapse. So first, I'm going to start with the architecture pillars that we took as guidance to build this distributed query processor. First is we built it for the data lake. And with that, we mean we want to query any data at large scale where it sits. For this, we had to define a data model, a flexible data model, such that the distributed query processor is abstracted from the storage engine and the underlying data format in such a way that we can generalize query processing over the data lake. Second is elasticity and resilience. The cloud is elastic, and by that I mean is that we can add and remove nodes from the compute topology as queries run. Therefore, through separation of compute and state, we built a stateless distributed query processor that can adapt to topology changes as queries run. So topology changes can be either self-induced, because we want to scale up and down the compute topology for cost efficiency, or they can be unexpected due to infrastructure upgrades or faulty nodes. Either way, we need to adapt to these topology changes and let queries complete. So now we have this elastic, highly scalable distributed query processor over the lake. But how about performance? So here is where we bridge the gap between big data systems and SQL data warehouses. We want to bring tier 1 performance of the appliance for factor, and we do that by leveraging for the backbone of query optimization and query processing SQL Server, which has 25 years of development gone into it. So with the shift to the cloud, there are many more variables that come into the place. We have multi-tenancy, we have multi-database ecosystems that run heterogeneous workloads with thousands, potentially millions of queries running concurrently. For that, at the core of the distributed query processor, we put a lot of effort to build a workload manager that can handle concurrency by task-aware query scheduling. Also, we want to autonomously tackle daunting problems such as capacity management, resource governance, and query access control without the need of an expert system administrator to do it for us. So let's now go a little bit more into the details on how we achieve querying any data over the data lake. So the data lake, it's a sea of files with a wide variety of data formats. So in order to generate query processing over this data, we define a data model such that we organize data file fragments as data cells. In such a way, the distributed query processor sees the data lake as a collection of data cells, and query processing acts on top of these data cells, oblivious to the underlying data format, which could be any from video file formats, BRK files, CSV, etc. On top of that, we also enrich metadata on top of these data cells through hash partitions and user partitions. Hash partitionings are used to speed up query processing in terms of some relational operators like vector aggregations or chain operations, and user partitions are usually utilized in order to prune or reduce the amount of data that you scan at query processing. Now, in the compute layer, when a T-SQL query comes in, it gets broken down into a collection of query tasks that are represented here as blue triangles in the slide. A query task has as inputs data cells. Then it has a source that it executes against the compute nodes, which is a fragment of the T-SQL query. And it also outputs data cells for the sake of interoperability with other query tasks. So through this association of data cells and query tasks, the execution of a query is scaled out across thousands of these query tasks. And the scalability limits, it's only limited by the amount of cells that we have in the data lake. That's by the amount of your data. So now that we have introduced this concept of data cells and query tasks, we can explain in a more simplistic way how we achieve elasticity over the data lake. So let's zoom out for a second, and in this example, we have 4 compute nodes as round figures with 4 query tasks assigned to each one. On top of this, we'll have the distributed query processor that will orchestrate distributed query execution. Now, in order to achieve elasticity, we need to have the flexibility to assign query tasks to any compute node as we want. And for that is when we introduce separation of state and compute. A state associated with compute means stickiness, and we need to remove that limitation from the system. So by state, we separate it in 3 dimensions. We have data, which we already said, we separate storage from compute through the data lake and the definition of data cells. And then we have other 2 forms of states, which are transactions and metadata, or transactional logs and metadata. And these are also centralized, or they're separated from the compute through centralized services that communicate with the distributed query processor and the underlying fleet of compute nodes. So that's it. Remember these 3 concepts. We have data cells to abstract the distributed query processor from the data lake. We have query tasks and the association with data cells, which give us this scalability to execute at large scale over the lake, and separation of state and compute. With that, now we can beautifully simplify the problem of elasticity over the lake as a bin packing problem of query tasks over the compute node that we have available for execute. So let me explain that by means of an example that enables for the user and the customers. So let's put in this example, we have 4 compute nodes, again, 4 query tasks on every compute node. And let's imagine that, let's say that there is times in the workload that we achieve peaks of load in that workload. So the distributed query processor in such case will be able to instruct the underlying fabric to add more compute to the compute topology, such that we can accommodate for those peaks in the workload. So, and we do that as queries run, such that the new queries or the new query tasks, they can be offloaded across the new topology that we got, and the previous queries continue running on the topology where they were already allocated. Now, for the sake of simplicity in the example, we just double the size of the topology, but the unit of increment can be just 1 node. Now, when the workload peak ceases, then the distributed query processor can then release the capacity that asked for in order to have a cost-efficient management of the pool. So let's go now through a second example of fault tolerance. So in order to scale at petabyte over data lake, we need to be able to recover from failures in the underlying compute topology. So we do that. So let's imagine we have this example where we have query tasks, again, running on the 4 compute nodes, and we have this a failure that we mark here as a red circle. So the distributed query processor will detect that failure, and then will just reallocate the query tasks that were assigned to that compute or that faulty node across the remainder of the healthy topology. And not that we just don't go to 1 node, but we actually are able to spread the load that we had in that faulty node across all the nodes of the topology such that we have a graceful recovery from node failures. So this is extremely important for us to achieve this petabyte scale that we are claiming, or that Rohan yesterday announced during the keynote, right? The reason is because in order to actually query over a petabyte of data, we need to be able to scale up to hundreds of nodes or even thousands that we have been able to do it, right? So at such scale, the probability of a node failure is much larger, and therefore, we must be able to recover from those failures without failing the query. So let's go through a third example, which is hotspot. So let's imagine again that we have these 4 query tasks on every compute node running, but there is some skewed load across the compute topology, such that this node, now that here are marked as yellow, we detect that it's heavily loaded. And we do that through a feedback loop with the distributed query processor from the compute nodes, such that we can actually detect that some slowness is happening in parts of the topology. So when that happens, the distributed query processor can react to it by rebalancing some of those query tasks across less loaded nodes in the topology. Now, what will happen if, for whatever reason, the hotspot still gets sustained? So now we can tie this back to the auto-scale feature that I presented first, and we can actually demand for more compute in order to remove that hotspot. And the unit of increase in order to remove the hotspot can be 1 node, or can be as many as we need in order to both remove the hotspot and improve performance. So separation of state and compute doesn't just bring elasticity to the distributed query processor in the cloud. It also brings other interesting features, such, for instance, the separation of transactional logs allows now that multiple pools can access and modify data concurrently over the data lake, right? So now we can have multiple endpoints actually accessing and modifying the same data. Then the separation of metadata also allows these compute pools perform cross-database queries across the data lake that it's also bringing as part of Synapse. So there are many more details that I'd like to explain and go into, but for the sake of time, we'll need to stop here. We'll publish a paper in a couple of months, hopefully in VLDB or CIMET, so look for that for more technical details, and obviously you can ask me or ask questions after the presentation. Thanks.
Thank you, sir. Yeah, so oh, look at that. I didn't get one of those when I transitioned to you. We'll take one at the end, I'm sure. Okay. So there's an interesting thing there about the hotspot that Joseph mentioned, right? The cloud gives us the ability to not only scale out. If you want to scale out and consume more resource, the cloud has you covered, right? But what's interesting about it is the scale-in capability as well. What Joseph showed there was 2 examples that will appeal to different classes of customer or depending on your scenarios or workloads. One where that you had a fixed capacity of effectively 4 machines, as it was illustrated, and when you hotspotted one of those nodes, we rebalanced across the capacity that you had. So we're looking to try and maximize the utilization of your capacity. And the other was then to say, actually, I'm in the cloud and there's a node sitting right there. I'm actually going to scale out. And what's really powerful about this is the incredibly granular scaling. Right? There's not t-shirt sizing to just say, hey, double, then double, then double, then double again. Right? What he demonstrated was you can have 4 nodes, and perhaps one of those nodes, the hotspot node, was running at 100%, and the others were pegged at about 50%. If you could unlock that one node, and because those other 50% are just being throttled because there's no more work to come because one node is pegged. If you can just unblock that one node and add 25% more compute, you could raise the utilization of all of your nodes closer to 100%. And so that's really powerful for really unlocking and giving you the biggest bang for your buck for the capacity that you're running in the cloud. So it's very, very powerful, very flexible, gives you the choice of both scale in and maximize and be a very predictable price, or scale out and leverage the elastic properties of the cloud. So let me now flip over to a second demo, and I want to talk now a little bit about data transformation, which I set up at the top of the session. You know, Joseph talked about how we can scale to hundreds or 1,000+ machines, and as you pointed out, the chance of the failure when you go to a lot of machines increases significantly. Right? This is just sort of statistics. But what's interesting is when you want to go and transform massive amounts of data, that distributed compute is critical, and there's also, of course, that recovery from failure. And so what we see customers doing, those who have been in the private preview, one of their common scenarios is really applying SQL to transform data at scale, but actually having no capacity to manage or worry about either side of that query executing. And because the amount of data that they're typically bringing into the system on a daily basis is relatively consistent, they're certainly experiencing very predictable usage characteristics of the platform, because we store the same query at the same data, and it takes about the same amount of time each day. So let me show you what that looks like here. If I just flip over again. So here I'm back in Synapse Studio, and I'm actually going to flip over to this CE test here. And I've knocked a couple of things out in green I don't need them for this demo, but what they are is an external data source that just helps me map to where I'm going to put this data, and an external file format that's telling me this is the format of the data that I'm going to go and produce. And so here you can see we're using Parquet as well. If I scroll down, you can see I'm going to create an external table. I've given it a couple of properties. And then I'm just doing a select star directly off this CSV location. What we find, and perhaps what you find as well, is data does not tend to arrive from external systems in the Parquet format. Most systems egress things as CSVs. That's sort of the format of interchange, or JSON we see a little bit more commonly as well. But to do performant analytics, you absolutely want to have these file formats in columnar optimized formats. Parquet is really becoming, I think, the dominant force in this space right now. Traditional relational platforms have leveraged columnar storage internally for many years now, and Parquet in the open community, I think, is becoming the dominant force. And so that's why we've invested so heavily to enable Parquet into the platform. What I'm going to do here, though, is I'm going to go and produce Parquet, because that's what I want people to analyze. It's more efficient, it's more performant, but I'm going to go and transform that from CSV. So I think I've probably run 4 already, so I'll just give that a 5. And we're going to go run this. And so this is now going to go and read the CSVs directly off the lake, and it's going to output Parquet. This is one of the most common things that I've seen customers go and use. Oh, they get an error. Oh, maybe I've already done 5. 6. This is one of the most common scenarios. All right. Oh, no, it's that one. This is one of the most common scenarios that I've seen customers doing with, there we go. So it finished no results, and it's finished the transformation. This is where we see customers spinning Hadoop clusters, putting them into pipelines. I've got unstructured data coming in. I want to turn that into Parquet format. This is one of the most common things that we've seen. And so now bringing this into a completely on-demand form factor in Synapse Studio itself, we think is going to help you streamline this very common task of transitioning data from the interchange format that typically exists in delimited and turning it into that Parquet optimized format. But if you've been past the booth, we will have also probably talked to you about the integration of Spark directly into Azure Synapse as well. And I talked at the top of the session around how we've enabled the meta stores to come together, that you no longer need to go and create this Hive table over here and produce something, copy the DDL over to here, copy the file over to there as well. That's not a scalable method. And so what we've done here, if I flip over to my Spark notebook quickly that I have in the studio, is we've enabled Spark to synchronize metadata directly into the on-demand catalog. And so here I've just got super simple Spark. The key syntax here is save as table. And so I'm going to just go run this quickly. I think probably give this a 7 as well, just to make sure I don't have a conflict. And I can go run this cell. And so now this is going to light up, and this is Spark on a Spark pool, reading data from my data lake, transforming it into something. You can see the Spark job running. But not only does it produce some data as the output, it also registers that metadata in my catalog. And so now I'm I'll put my data scientist hat on, or my data engineer hat on for a second. I've gone and done this work in Spark, probably far more complex in the real world. I've produced some really valuable insights that people want to consume via a SQL interface and do their day-to-day job. And so I produced what here was enriched population V7. If I flip back into data now, and here is my on-demand database, I'm going to pull this out. You can see the ones I did previously. And there it is. And so now I can then go and click on the little ellipses here, put on my SQL analyst hat, give me the top 1,000 rows, and this is just SQL running directly over the Spark that I created. All of the catalog coordination is handled for you, and you don't have these previously laborious tasks of needing to manage different catalogs, DDL, and everything like that. Okay, there we go. I should stop there. So we have a couple of case studies here from customers as well. Agreco is actually one who has been previewing Azure Synapse. They've been using the SQL On-Demand capabilities. This is a public case study that's on the Synapse website today, so you can take a look at what they're doing. Perhaps you can think of this maybe as more credible or less credible. Customers always ask us if we use our own technology. We absolutely do everywhere. Dynamics 365 is leveraging the SQL On-Demand capabilities today for a lot of their analysis. This is a quote from Anil, who I believe is probably in the room somewhere as well. So Anil will probably be floating around at the end if you want to understand more about how we're consuming the technology ourselves in Dynamics to do analysis under the covers. You, as a Dynamics customer, you don't see it, you don't know that you're using it, but we're absolutely starting to use Synapse in a lot of our line of business applications as well at Microsoft. The call to action, of course, as we start to wrap up, is go sign up for the preview. We obviously want to get as many people onto the service as we can. Come by the booth, visit us. The public service announcement is we're out of hoodies. Sorry. They went very, very fast. Lesson learned, very popular item. We'll do more of those next time. We have a ton of sessions that are on as well at the moment throughout the week. So take a quick look at this and see where the next Synapse sessions are. Fortunately, Synapse is not a term that's commonly used by any other service at Microsoft. So if you search the catalog for Synapse, you'll probably find all of them. And then we have other series of sessions as well. And then there are theater labs as well. But absolutely, please come by the booth. We're heavily staffed, and we'd love to talk to everyone. And we've got a lot of demo stations set up where we can take you through even more extensive content than we have today. So this is pretty much everything we had. It was a bit of a split session. We wanted to describe just the basic functions of SQL On-Demand, and also, of course, how we built this technology to run at the scale that we've described this week. I'm happy to take any questions right now at the mics, or normally if you want to come up to the stage as well, either myself or Joseph will hang around for as long as need be. So thank you very much. Appreciate your time.